Today we will discuss a very popular statistical tool that is called regressions. And actually, there are different kinds of regressions, and what we will be discussing today is bivariate OLS regression, to be exact. So this is more or less a similar story to the story of previous lesson. At the previous lesson, we discussed that if we have two numeric variables, then we may be interested in some relation between these variables. We may be interested in question like, for example, we have two variables like, for example, read and math. So these variables denote reading and mathematical score of some students. So every point at this graph corresponds to, for example, one student. And we discussed the story that it is possible that there is some positive correlation between these two variables. That if we see a large value of reading score, then we probably will see also large mathematical score as well. And vice versa. If we see small reading score, we see also small mathematical score. And this idea that two linear variables can be related in this way is it can be discussed in terms of correlation, as we did at the previous lesson. So a short recall. That we discussed regressions, that we discussed correlations, correlation coefficient. And this correlation coefficient denotes how close our points to some straight line. I can say that this correlation coefficient shows in some way it shows that we have strong or weak relation between two variables. So correlation coefficient measures, I can say how obvious the relation is. So how easy to see this relation when we look at the graph. And what we also discussed, just let me recall the formulas for this correlation coefficient. Assume that we have two variables, x and y. And we have some values here, x1, x2, and so on, xn, and y1, y2, yn. And we discussed that Pearson's correlation coefficient denoted by R usually is calculated in the following way. It is something like okay, I would avoid using this summation sign. and we divide it by standard deviation of x times standard deviation of y. So here x is just a sequence x1, x2, and so on, xn. X bar is just an average, and the same with y. Let us look at this formula. What happens with it if I, for example, increase, for example, if I multiply all values of x by 10. So what happens with R? If we replace all values x by, for example, 10x. What happens in this case with the value of this R? This was discussed briefly at the end of the previous lecture, but let us look at the formula and see what happens in this case. So first of all, what happens with x bar? If I replace x1 and so on xn by 10 x1, 10 x2, and so on 10 xn, what happens with x bar?
The bigger,
Yes, how much bigger?
10 times.
10 times, yeah, exactly. This is correct because just you can look at this formula and you can see that if you have 10 x1 plus and so on plus 10 xn over n, this is just like 10 times x1 plus and so on plus xn over n. You can move this number 10 out of this expression and just put it near this fraction. And so we see that indeed this will be multiplied by 10. And then what can we say about the numerator of this formula? So we have something like 10x1 minus 10x bar and so on.
The lower than before the operation.
Actually, you can again move this 10 out of this bracket. You can move it out of this bracket, and then you can move. You have 10 something plus and so on 10 something, and so you can just move this 10 out of the whole bracket, so it will be multiplied by 10. Oops. So numerator will be increased again by multiplication by 10. It will be 10 times larger. And what happens with the denominator? So a standard deviation of y will not change because y is not changed at all. And what happens with standard deviation of x? Again, this is actually rather important. Let me recall that standard deviation of x is square root of the following thing. Hmm? And so if we replace again x by 10x, we see what happens with standard deviation. First of all, what happens with the value under the square root? Yes, we can move 10 out of the parentheses, but look at this. Look at these squares. We see that if we write it down like this, mm-hmm. Yeah, we have the same thing as as like 10 to the power 2 times x1 minus x bar to the power 2, and so on here. And so we have this 10 to the power 2, but when we take a square root, so basically you can, okay, so basically you can move this 10 to the power 2 here, and then you can write it like this. This is square root of 10 to the power 2 times this is what we had before. This is just a standard deviation of x, and this value is just 10. So we see that if we multiply all values of our sample by 10, then standard deviation is also multiplied by 10. So it is a long calculation, but calculation is rather elementary. We just used some high school techniques, high school algebraic techniques, like factorization of products. So are there any question about this transformations?
Could you repeat your conclusion? If we multiply what by 10, we multiply what by 10.
Okay, let me summarize. So initially we have this this value, and let me rewrite it here. Oops, sorry. So this is numerator, and this is denominator. Then I replace all our x's. I replace it by 10 x's. So basically, I just multiply all the values by 10. And what happens in this case? In the numerator, we have we have 10 times the same thing that we had previously. Okay, let me write it down like this. And in the denominator, again, we have 10 times standard deviation of x. Sorry, there is error here. So we see that numerator and denominator are replaced by 10 times in the initial numerator and denominator. So these values just cancel each other, and we have the same value that we had before.
So this was the Pearson correlation coefficient, and I understand that if we multiply it by 10, nothing changes, but maybe I have two questions. So why should we multiply it in the first place? What we expected when we did this?
Just let me write it down like this. That if I multiply all values of x by 10, then correlation coefficient doesn't change. And the same happens if I multiply second variable by 10. And of course, I can replace 10 with any other non-zero number. Why we are interested in this transformation? In fact, what does it mean that I replaced all my values by the same values but multiplied by 10? This is like just a change of units of measure. For example, if we measured something in meters and then changed units of measure and now measure the same values in centimeters, then it just means that we multiplied everything by 10. So it is possible that we have initial data frame where x is measured in centimeters and y is measured in centimeters. And we have something like this. And then we can change, for example, units of measure of x. And, sorry, let me do it vice versa. X is measured in meters and y is measured in meters. And then we change units of measurement, and now we measure everything in centimeters. And then it means that we have just to multiply everything by 10. Sorry, not by 10, but by 100. So I'd better use different values, different units, decimeters here. So the idea of these formulas are the fact that the correlation between two variables does not depend on units of measurement. We can change units of measurement, and correlation will be the same as previously. And visually, it means that if you have, for example, this picture, and if you multiply all values of, for example, y by 10, then the picture will be changed. It will be something like this. But the correlation coefficient will not change. So it means that correlation coefficient does not depend on the slope of this line. So correlation does not depend on scale of axis. So just correlation just measures how close our points to some straight line, and they do not measure what is the slope of this straight line. And sometimes we are interested in correlation, but sometimes we are interested in the slope of this line. Sometimes we are interested in answer for the following question. How fast y is changed when x is changed? So to answer the latter question, we have to use different statistical tool. And this tool is called regression analysis, and that will what we will discuss today. So correlation does not detect slope of line. How fast y changes when y changes. So yeah, if we are interested in the answer to this question, we have to use regression. So let me show you some possible data set, some possible setting when this question is very natural. Assume that we are interested in the following question: how fast children learn new words. And for example, we can create a data set. We can select some children who wish to participate in this kind of study. And probably we will have children of different ages, not just one specific children that we communicate with during a long time, but we just have one experiment, but with children of different ages. And we have a table like this. We have child, and we have age, and we have, for example, vocabulary size. I don't know which numbers will be realistic, but let us pretend that I will put something. Okay, when children begin to speak.
Around 1 year old, some very early, around 2 years old, maybe it's also early, but I think maybe
Okay,
it will be.
Okay, let us assume that we have some 1-year-old children who do not speak, and we have some 1-year-old children who has 10 words in their vocabulary, and we have some 3-year-old person who has 100 words in their vocabulary, and so on. So we will get some data set. Probably it will look like this one. And horizontal axis is age, and vertical axis is vocabulary size. So we can ask a very natural question. How fast children's vocabulary increase? So we are interested in some sort of velocity. We want to make some answer to this question, and this answer can be stated like at every year, children usually teach, for example, 100 new words, something like this. I do not pretend that I'm correct with my estimate with my numbers, but this is just an example of the question that we can ask. So how can we answer to this question? Are there any ideas? Let me restate it in the following terms. How many words do they learn each year? How can we answer this question by looking at this data?
So I have a question. Children A, B, and C. There are different children. So
yes. They are different children. We just have a group of children. So we do our experiment just once, but we have different children of different ages, and so we want to use this information to answer this question.
So can we say that to the age of 3, children learn 90 more words than comparing?
Well, if you just subtract this number from this number, you consider just two children. But we have much more data. Actually, this is just the beginning of my table, but we have much more table. So basically, when you see, so probably these 3 rows correspond to this, and these data points. But according to this table, according to this picture, not all students of age 3 know 100 words. Some of them know less than 100 words. So we can pretend that we have here 100 and here we have 10. And we see that there are children who know less than 100 words. So you cannot just subtract this from this to answer the question. You have to You have to take into account the whole data set. I just want to stress that correlation coefficient that we discussed previously does not answer this question at all. In fact, this is because the answer to this question, how many words they learn each year, is denoted by the slope of some straight line. And assume that I have new data, and in this new data, all values here are multiplied by 10. Then it means that with new data, we have to conclude that number of words that they learn each year is multiplied by 10. Yes, if I just replace everything here, but by the same value but multiplied by 10, then it means that the velocity is multiplied by 10. So you cannot use correlation coefficient to answer this question. Yeah, we are interested in the slope of the line, and let me just make some short short recall. About linear functions. This is actually the main function that we will use. And let me recall how do they work. And let me consider the following straight line. So I have values 1, 2, 3, 4, 5. First of all, this is a straight line. At least I tried to draw it as a straight line. And as you probably remember, straight lines are given by formulas like this. Y equals to kx plus b. And so the question is, please answer me to private messages. The question is, what is the value of k, and what is the value of b at this picture? So, any ideas? What are the values? Okay, 2 and minus 1. Let us look at these values. Indeed. First of all, it is easy to find the value of b, because what is the value of b? If I substitute 0 here instead of x, I will get the coordinate of this point, because this point corresponds to 0 of variable x. So let me denote it also by f of x. So f of 0 equals to k times k times 0 plus b. And this is b. So you see that this is exactly the y coordinate of this point. And this is b. This is free term of our linear function. But actually, we are not so interested in this free term, but we are mostly interested in this k. Because what k shows? It shows the following thing. If I increase, so let me put some point, for example, this point. If I increase value of x, I will make one step to the right, and then to stay on the line, I have to increase value of y. So this is x increment, and this is y increment. And we see that if I make one step to the right, I have to make two steps to the top. So I have to increase y by 2 when I increase x by 1. And this happens at any point of this line. So if I draw the same, for example, if I draw the same picture from this line, this is the same thing. I make one step to the right, and I make two steps to up. And basically, if I look at the formula, I see that if I have f of x plus 1, it is equal to k of x plus 1 plus b. And then I can expand this product, kx plus k plus b. And then I can say that this is kx plus b plus k. How can we denote this value in terms of this function f? What is this thing? So what should I put in? What should I put into brackets? What should I put here? This is actually at the white bar right now. So I denote by f this dependence. F of x equals to kx plus b. So what should I put here?
X plus b. No.
No, look, f of x is kx plus b. So
ax plus b plus 1.
in fact, yeah, I have to put here just x. And my formula stands that f of x plus 1 equals to f of x plus k. So it means that if I increase x by 1, value of y is increased by k. So we see that this k is exactly this distance. How far should I change value of y when I increase the value of x by 1? In other terms, this case shows how fast y increases as x increases. So, for example, for example, if we think that x is, for example, age, and y is number of words on the size of vocabulary, then this k is exactly the answer to this question. So let me show it as an example. Assume that okay, um, let me return to this picture, and let us assume that we have some straight line that is, in a sense, best fit to this data. And this straight line looks like this one. And then this straight line is also given by some equation like y equals to kx plus b. And again, we can interpret this value k and this values b, at least try to interpret in terms of this problem. Let us forget for some time, let us forget these values of our data. Let us look only at this straight line. Let me put age here, vocabulary size here, and let me pretend that the actual dependency is given by this straight line, and I have some values. For example, I have here at age 1, I have 5, and at age 2, I have, for example, 55, and at age 3, by the way, how many words will be in my vocabulary if my dependence is linear? So if it is a straight line, and I have these values as shown. So what should I put here?
105.
Mm-hmm. Yeah. How did you find it? So, and what can you say about k and b if I say that y equals to kx plus b, or vocabulary size equals to k times h plus b. Okay, can you find these values k and b now from this picture?
So B is 50. Yes.
B?
Not K is 50.
K is 50. Yeah. K is 50, and actually k is this difference. So we have one step to the right, and we have 50 steps in the upward direction. So this is k. And we see that the same thing we have at the next step, and so on. Yeah. So if we want to find the value here, actually, if I believe in these numbers, then I have to say that b equals to
Minus 45.
Yeah, I have to make one step to the left. So it means that I have to make 50 steps to the bottom. My picture is not very accurate, so it is a little bit misleading. Let me try to redraw it more accurately. It should be like this. And so b is 5 minus 50. So it is negative 45. So again, if I return to my question about how fast vocabulary size increases with age, the answer for this question is this value k. It is exactly the value that shows how many words our children become familiar with at each year. So if we have size, vocabulary size equals to 50 times age minus 45, we see that this is how fast they learn, or how many words they learn each year. So this variable, actually this parameter is called slope. So this is slope. And how can you interpret this value, negative 45? What can you say about this value b?
Just strange that they know some negative words before they born.
Yes. Yes, in a sense, this value doesn't have any good interpretation in our model, because we understand that our linear dependency doesn't work, for example, here, because it predicts that just when our children born, they have to know negative number of words, which is obviously impossible. But it basically it is not some problem with our data. It is just an effect that shows that that our model is not applicable everywhere. Our model can be applicable, for example, at this age, 1 to 3 years, but can be not applicable, for example, here or here. Probably people of when people become adults, they does not increase their vocabulary size so fast as students do, as children do at the beginning of their life. Yeah. So we are usually interested in this coefficient. Sometimes we are interested in this coefficient, but it is much more rarely, and we have to interpret it correctly. So basically, what I just shown is what we do when we say that we want to fit a regression, some linear regression to our data. Let me recall how we do it. We have some data, we have some data points, some values of x and y, and then we fit some straight line, and the equation of this straight line is k x plus b, and the values of k and b. So basically, if you have different straight lines, they have different k and b. And so to choose a line that fit our data in the best possible way is the same thing as to choose this k and b. Fortunately, we do not have to do it manually, and R will do it for us. It will find the straight line that is, in a sense, best fit to our data. Of course, not all data points lie on this line, because we have much more points and that can lie on this line, and we don't have perfect correlation between age and vocabulary size. Even children of the same age can have different vocabulary size, but uh, we try to do our best to fit this straight line to our data. Then we find this k and b, and then we can interpret these values in terms of our initial problem. For example, for this kind of data, we have k that just shows how fast how fast children learn new words. So this is what we have with this regression. Let me discuss a little bit how to fit the best line. Okay, let me just summarize what I've just said. So basically, we have data. Some points. Then we fit straight line to our data. And then we interpret coefficients. like k is how many words? They learn each year. So this is two steps that we usually do. First, we fit our model, then we interpret the coefficients that are given by this model. Do you have any questions at this point? Just before we start discussing how we can find this straight line. Okay, then we can probably continue. So how to fit best line? This is done in the following way. We have some points. And then we try some line. For example, this line. And then we can find how far our points are from this line. So to do it, we can find the difference between y coordinates of these points and the corresponding points on this line. So let me assume that this line is given by some equation y equals to kx plus b. And then we have differences like this difference and this difference. So I just put straight segments of straight vertical lines. And these segments are called residuals. In fact, it is easy to find the value of these residuals using just formula. So let me assume that, for example, this point is point x1, y1. What can you say about this residual? What is the value of this residual? If this is the point with coordinates x1, y1, and we assume that this straight line is given by this formula, y equals to kx plus b, where k and b are some fixed, at least for a moment, fixed coefficients, fixed values. So can you find this difference? Just writing down as the formula. Any ideas how to find this difference?
Just subtract
Mm-hmm.
y2 from the
What?
kx plus b.
Mhm. Yeah, I have only y1 here. So this is y1,
Okay.
and this is y1. Um, mhm. Yeah. First of all, I have to find this value, the y value of this point, and this value is given by my formula. So I just have to put x1 into this formula, and I have x1 k x1 plus b. And then I have to find the difference between two values, this value and this value. And so this difference is given by kx1 plus b minus y1. And of course, we can do the same thing with any other point. So we can find the residual at each point. And how do you think what we want to do now? We have these residuals. So there are some values. What we want from these residuals, we want them to be small or large.
We want them to be small.
We want them to be small, yes, because this residual is just a kind of error. It shows us how far our straight line, our model, to our data. So we want them to minimize. And in fact, the problem with these residuals is that they can be positive or negative. And if we have a very negative residual, it means like that we, for example, somewhere here. And it is not very good if we have very negative residual. So we want them not to be small in sense that negative, but we want for them to be small in sense close to zero. And it means that we want to replace negative terms with positive terms, and we can do it as usually by taking squares. And then we want to make them small. Well, in a perfect case, we want them all to be small. But we also understand that it is impossible for them to be small at the same time. So we minimize not every individual residual, but we minimize the sum of their squares. So we want to minimize this thing. So we just we can change this line, and every line gives us its own values of these residuals. Note that your data is fixed now, and you just try to find the line such that this sum of square of residuals is as small as possible. And this is actually how ordinary least squares method work. In fact, this is called ordinary least squares. Or OLS. So it is called least squares because we have these squares of residuals, and we minimize them. We minimize its sum. And again, basically, it is not very difficult from a mathematical point of view to provide exact formulas for these values k and b that will minimize this sum. But it is rather, well, it is not difficult, but we will not waste our time in finding this formula because it is already implemented, of course, in our package, and we will just use it. So what will happen? In fact, this step will be completely automatic. You just put your data, and R gives you this straight line. In fact, it gives you these coefficients. And then your problem is just to interpret these coefficients correctly. So this is how regression analysis usually works. Are there questions so far?
So when we found these residuals, so what does it give us? So
In fact, we can interpret these residuals, but in fact here I didn't discuss how to interpret them, but I just said that when we find this best fitted curve, best fitted line, that we try to minimize these squares of residuals. So they are important not just by themselves, but they are important just by as a tool that allows us to find the this best fitted line. In fact, there are some questions that can be answered about the residuals, and we will probably discuss them a bit later.
I have a question.
Yes, sure.
So, but this model, we can only have one independent variable.
Yes, actually, today's lecture is devoted to bivariate regression. That is a regression with one independent variable. Exactly. At the next lecture, we will discuss what should we do if we have several variables, and how can we interpret them. But today we just consider the simplest case when we have only one x and one y and nothing more. So again, this story is a story about finding this optimal line. I just say that I can take any line. For any fixed line, I can find this sum of squares of residuals. Actually, this can be done by just finding these distances and finding their squares and finding the sum of their squares. And then from the whole set of all possible lines, I select one straight line that minimizes this squares of residuals, sum of squares of residuals, or residual sum of squares. So this is just an algorithm of fitting.
okay, so I understood that by finding k coefficient, we can find the velocity of change, and what this fitting of line give us to the velocity, etc. So why should we fit this line? Why we have this problem? Because in the first one it was linear and simple, and everything fit in the same. Okay.
So we begin with the data, and we begin with the question like this: how many words do they learn each year? This is our question. And then we say, okay, if there is some, okay, we replace actual real students or real children with some model. We assume that there is such number, just one number, that shows how many words, just like average child, learn each year. And then we find some estimate for this value. We do it by fitting this straight line. So this straight line is, in a sense, a kind of some average children, average child, and we just try to find how fast this average child will acquire new words. So this is our method. I'm not sure that I answered what you were asking.
So yeah, and so we drew this straight line, and then we can find the velocity of change, and then by applying the ordinary least squares method, we can find how much we are mistaken. Yes, because the more this coefficient is, it means that we are more mistaken because we drew this line in the wrong place. Yes or no?
The more this thing, residual sum of squares, yes, the more our mistake. This is some of our mistakes in a sense. So we want to minimize it. When we minimize it, so when we find the straight line such that this sum of our mistakes is as small as possible, we say, okay, this is the best model that we can find in our class of models. And after that, we interpret the value k of this line as the correct answer. Actually, some estimate for the correct answer. For this is the some estimate of an answer to this question. So we after we fitted this line, this best fitted line, we just get this k. This is this k is obtained just we fit this line. So this is how it works.
So every time, perhaps we should draw at least two lines to compare which OLS is
Well,
more.
it is done automatically. There is algorithm that allows us to find exactly the line with the smallest residual sum of squares. So we can just write down the formula that allows us to find the line, so values of k and b, such that this thing is as small as possible for some fixed data.
Okay, yeah. So yeah, I see. So this OLS method help us checking our results. Yeah.
In fact, it allows us to find the result. Okay, let me show you some example. Assume that I have data that are like this. For example, so can you guess probably the equation of the best fit line? How do you think?
So it should be um, one one. So x equals 1 and y equals 2 in the first dot. So and the third dot should be x equals 3 and yeah, and y equals 3.
Exactly, exactly. In fact, this is a straight line like this. And can you show me? Can you find me the value of k? So if I have this equation, what is the value of k?
One.
Mm, If it were 1, then
it's not 1.
Yeah, if it were 1, then I have to make one step to the right and one step to the upward direction, and I will not get into the line. So what is the value of k in this case? In fact, I can make 2 steps to the right and make 1 step.
So it's
up.
one half.
One half, exactly. Yeah. So in fact, what we did just now is OLS estimate, because in fact this point is the best point from the perspective of if I just try to find sum of these residuals, sum of squares of these residuals, then the best point that minimizes sum of squares of this residual and this residual, the best point is in the middle. And the same here. It is also in the middle. And so we have to put a straight line just exactly as we drawn here. K is not 1/3 because here we have to make 2 steps to the right, not 3. This is value 3, but we begin with 1, so we make 2 steps to the right and one step up. So basically, the problem that is solved by R when it finds this best fit line is very similar to this one, but just a little bit more complicated.
I have another question also.
Hmm?
If I have another question.
Yes.
If I don't need to find this coefficient k, then this just a correlation. The same as correlation.
Probably yes. If you are not interested in the velocity, in a sense, in how fast y increases when x increases, then you probably are interested just in correlation between 2 variables. Yes. Okay. More questions?
So when we return to the beginning and talking about these centimeters and meters and different units of measure, so what does this what we discussed gives us? So it could show us.
That's a very good question. Yeah, as we discussed here, if we change units of measurement and, for example, multiply all values of x by 10, then nothing changes for correlation coefficient. But let us look here. What happens, for example, let us look here. What happens, for example, with value k, if I would measure vocabulary size not in words, but, for example, in hundreds of words. So if instead of this table, I will consider a new table that it will be like this. So again, I have age and I have vocabulary size, but now it is hundreds. And I will get data like this. Something like this. What happens with my coefficient? What happens with my coefficient k in this case? So now I have a straight line again that is like this. But now all these values are increased by 100 times. What happens? What happens with the coefficient? In another terms, how fast, how many? So k now. If I have again some equation like this, then k is the answer for the following question: how many hundreds of words they learn every year? So what is the difference between this k and previous k? So if I know that, for example, my children learn 50 words each year. How many hundreds of words they learn each year?
One half.
One half. So it is decreased from 50 to one half. It is decreased by 10. So this coefficient that we get from the regression model, this coefficient is not unitless like regression coefficient. Sorry, like correlation coefficient. In fact, this coefficient has some units of measurement. In fact, in this case, k is measured in hundreds of words per year, something like this. And so if you change units of measurement, you change this k. It means that if I rescale this picture, for example, by rescaling vertical axis by stretching or something like this, then the slope of this line will change. And this means that I will change this k. Did I answer your question?
So k is divided by 100, yes?
Yes. In this case, k is divided by 100. Yes.
Okay.
Just think about this question. So think that you have two k's. One k is how many words they learn each year. And another k, let me denote it by something like k with tilde. Is the question, is the answer for this question. Just think how this value k and k tilde are related to each other. So if, for example, if k equals to 50, then k tilde equals to 50 over 100, it is 1/2. So regression coefficients are sensitive to this rescaling. This is just a different tool. This gives just different information about our model, about our data. Other questions? Okay, if there are no more questions, I think we can stop our lecture now and make a 10 minutes break and then practice with regressions. Okay. So 10 minutes break from now.
I would say that it's more like a start.
Hi, everyone. How are you?
Okay.
That's good. How do you feel about linear regression? Have you heard about that before, or maybe even used it before?
I think not,
It's hard
but
to use it in
So,
reality.
so in theory, you know it, but in practice, you maybe have some general feeling about it, but not know some details, right?
I just mean that the linear correlation is hard to find in linguistic data.
Sorry?
Excuse me, you can hardly hear me. I just mean that it's a really rare case when we find such a pretty linear correlation in linguistic data.
Yes. But also what you can do if you don't have linear correlation, linear relationship between your data, you can transform your variables. Actually, if you have no linear relationship, but you see some relationship, but it can be some log linear or exponential or whatever, actually you have three main things to do. First, you just avoid some parametric methods and just use some non-parametric methods, like, for example, maybe you remember something that you can do if you, from the previous lecture and seminar, what you can do if you want to test non-parametric association between two variables. I mean, non-parametric means that you don't have linear connection between two variables, but you want to check the hypothesis that the higher is one variable, the higher is another, but it can be not linear, but at least it is monotonic. So, I mean, the function describing two variables is somehow increasing or decreasing, but it's constantly increasing or decreasing, maybe not in the same rate for all intervals, but it goes in one direction. So, do you remember? I mean, it's important.
We discussed Kendall methods.
Yes, Kendall and Spearman. Kendall and Spearman, Pearson for if you have linear association between the variables, but if you have some outliers, if you have nonlinearity, you can use Spearman or Kendall. It's one option what to do when you have not linear association between the variables. Another one is actually transforming the variables. It's a complicated question. It's really discussed. It's debatable whether it is a good idea or not. But intuitively, it seems that it's something criminal when you transform your data. For example, if you logarithmize the variable. In fact, that's really not so much a problem usually, because you can still test your hypothesis, but you should be aware that you interpret not now linear relationship, but some logarithmical relationships. But still, there are some other problems. Maybe if you have some, for example, I mean, it's important what exactly transformation you apply, because not all transformations are good. So there are, for example, many family of transformations that just normalize your data, meaning that they transform your data to be more close to normal. They call box-Cox transformations, or and also the most modern option is Yao-Johnson transformation that is actually can be applied also for negative values, but it's actually very debatable too, because maybe your data are non-normal for some reason. And actually the final way to deal with it is actually application of more complicated models. But all these more complicated models, they're usually based on linear regression or more general linear model. It's something like a framework that combine both linear regression and actually it's basically just multiple linear regression, a bit with some more advances. So basically, general linear model, if you've heard about it, basically it's just a regression formalized. And that's why it's very important to understand linear regression. And it's very basic method. Even if you want to study nonlinear relationships, yes, you'll use something like generalized linear model or even generalized mixed effects models. But you know, it's generalized mixed effects models is generalization of a generalized linear model. Generalized linear model is generalization of a general linear model, and general linear model is a generalization of just a simple regression. So that's why it's important to understand what's happening in regression, and that's why we'll use we'll explore it today, and we'll try to not only understand how to implement it in R, but we'll also try to play with it. We'll try to take some how to say, prepare it, you know, like how anatomists prepare body, in the sense that we'll cut it on small pieces and try to investigate it in details. Okay, so basically, I'm sorry, I need to share my screen. Okay, so again, library tidyverse, and we'll work with the same data set as we used previous time, the school data set. I will send you in a chat the code, and don't forget about library tidyverse, of course, because we will work with tidyverse. If you will have time, but I'm not sure about that for today, we'll also learn a bit more about tidyverse too. I want to cover merging or joining data frames together, but I'm not sure that we'll be able to do that today, because linear regression is a pretty pro topic. Actually, it's very easy to do linear regression in R. So maybe you actually found out that actually implementing all these complicated statistical things in R is just one line of code. It's that simple. But it is a bit different compared to test functions that we used previously. So first, let's think about what we want to use for regression. So Well, I have an idea. Maybe you have a better idea, but we can start with this idea, and we can do something later more. Let's explore linear regression of writing grades with a predictor by reading grades. So whether reading can predict better writing. So yeah, again, we use this words predictor, outcome, and it's important to remember that it's just words, just the terminology. If we call something a predictor and another variable outcome, it will not bring causal force, causal causality to reality. So we actually still exploring correlations. And it's important to remember, and you need to keep in mind every time you read that something predicted something. Predicted means sounds like X is cause of Y, but it's actually not the case. We have just a connection between the variables and nothing more. You can talk about causality if you do an experiment, or maybe, I mean, if you don't have an experiment, it's very hard, it's very difficult to talk about some causality hypothesis. You can, but it's very tricky and you are not sure usually, and so on. If you do an experiment when you control some variable and then record some response, well, you can talk about causality. You can explore causal hypothesis in neurolinguistics, in psycholinguistics. You can just give different stimuli to subjects. You can give them correct words, or I mean real words and pseudo words, and compare response, compare event-related potentials, for example, right? It is an experiment. You can manipulate things and record a response. And in this case, you can talk about causality. But if you compare something in different, I know, for example, languages, and you cannot just influence the language. I mean, well, maybe if you are popular TikToker or Morgenstern, or I don't know, you can somewhat, but it will be not really experimental, I think. So it's complicated. Who was the guy who really influenced Russian language for the last time? Do you have an idea of someone who really changed something in how we?
By influencing the language, you mean invented new words?
Invented new words, at least. I think it's the most common thing that you can do. I know Северянин, but it was 1 century ago. Okay, let's go to linear regression and to LM function. LM stands for linear model. It's the main function for regression. And here we have a very specific syntax. Here we work with columns in a data frame. And the first argument is always a formula. So it's formula, it's just an argument for the function LM. And let's say we want to do like reading on write, and predictor is always after the tilde. I mean this tilde, it's where you have letter yo or backtick. It's usually on the left up top left corner of your keyboard, or maybe on the left bottom. It depends. And right to the key that we always have predictor. And we want to use read here. And on the left side, you have outcome. Let's say right. Then you need to say data. So the data set that you use. And let's run it. Let's see. And okay. And what did we receive? What do you think? I will start to draw this dots. From point is red. So yeah, I ask you, what is it? What are these coefficients? What is this? What are these numbers? What do you think?
Intercept is the score. It's not look like, doesn't look like score. No, it's a score, minimum score for writing.
It's not minimum score, actually. It's
Yes, because
yeah.
they are all whole numbers.
So what is it actually? I mean, in theory, what are these two numbers?
Probably the second one shows how the effect.
Yeah. So the second one says these two coefficients are coefficients of this line, this linear regression. So every line you can define with the two numbers, intercept and the coefficient for x. So this formula you remember from the school, I think y is yx plus b, right?
So intercept is
and sorry, yeah.
The intercept is meaning of y when x is 0. Yes.
Yeah. Right. And we'll check it now, actually. Let's write this line. The plot. Okay, you can see this. The plot, let's do like in minimal. And also we'll add some alpha here. Yeah, it looks better. I would add also some jitter because, you know, there are many actually dots that are just right one on another. Maybe you'll see it if you have lower alpha, or maybe if you use jitter. I don't know, I don't want to use jitter here. So we just added some small noise to add it more like a crowd of dots. But okay, let's do it without jitter, but with some low alpha. Okay, so actually what we can do, we can use these coefficients. LM, let's say model, model, right. And we can use these coefficients from AB line, and I don't remember how it's used. I think it's slope and intercept. Yeah, slope and intercept, right. So what we take for the slope, which number? I mean, one of these.
The effect and 0 dot.
Yeah, exactly. We can even take this object and remember that actually Objects in R are usually just if you have some complex object, for example, output of LM function is just an LM class, object of LM class. But if you explore what is inside, you will find that actually just a list of 12 items. And actually you can even like take some results of this linear regression from this object. And it's very important actually still when you work in R to explore objects of some that are created by some functions for modeling, because it gives you a lot more flexibility. So for example, if you want to use these coefficients to draw the line, right? So instead of just copy pasting, for example, that is not really flexible, you can use, for example, here is just a name vector of length 2. So for the slope, we use this one will be red, and for intercept we use model right coefficients. Oh, I forgot this. I had an extra white space. And for intercept, I use the same model right coefficients, but 1, because the first one is for intercept. Okay. And let's see how it looks like. Whoa, just a line. And do you think that it is a good line for this data? I mean, just express your opinion.
It's a straight line.
Well, data too far from the line, but how do you change a line? How do you, I mean, how do you fit if it was your choice? So actually, yeah, when I ask you about is this line good, you can ask me, I mean, in what terms good? How do you measure goodness? What do you use for goodness here? Line is great, but it's not representative enough in my opinion. Yeah, that's a problem of linear regression, because maybe relationship is not linear. Maybe we actually, of course, we have a lot of noise there. And maybe it's not just like meaningless noise. Maybe we can explain it somehow, but maybe we can't. And it's actually, it's interesting topic, because actually linear regression, it's not only very basic and important method in statistics, but it's actually one of the most used methods in machine learning. Yeah, actually machine learning is more or less the same as statistics, but you know, the different fields, and actually they usually have different purposes. And they usually use it a bit differently, because they have some own rules how to use it. But basically, the method is really the same, and mathematics is the same, and logic is the same. Yeah, and when you talk about these errors, these residuals in your data, you need to understand that actually there are two sources of this non-explained variability. Something that we can really explain with our data, with variables that we have, and something that we cannot explain. And you can easily imagine that you, with all these variables that you recorded, you will never explain everything in your data, because every data point here is individual, is very complicated person with his own intentions, problems, family situation, environments, and so on. And we cannot just use all these variables to make a perfect prediction of writing scores, for example, right? We cannot do a perfect model for that, and we need to just be okay with it. And we need to understand that we have some threshold. Above that threshold will not be successful anyway. And we need to minimize errors that we can explain. But if we try to explain errors that is not reducible, we are doing something wrong. So we need to like maximally explain what we can, and do not try to explain what we can explain, because actually you can do not linear model, but some very complicated non-linear function. For example, functions that will draw a line between all these dots. But will be a better regression? No, it will not. And it is called a problem of overfitting. Maybe you heard about that. It's very very popular term in machine learning. So usually the simple models are the best. So yeah, maybe you have maybe you do not explain a lot, but at least you explain something, and something that is more than nothing. And yeah, we need to be like okay with it. So okay, let's return to our model and our graph and idea of linear modeling. And actually, when I ask you about whether this model, whether this line is good, you can ask me, but how we measure this goodness? And do you remember how we measure this goodness? Actually,
By Pearson correlation?
no. I mean, when we talk about this line, I mean, what?
Ordinary least squares method?
Yes, exactly. Ordinary least squares. So actually, you have something that you explain with your model and something that you didn't explain. And you can even measure the quality of your model by comparing what you explained and what you didn't. So actually, let's see actually summary for this model. We'll use not just model right, we use summary on this object. Remember, summary is a generic function in R. It means that you can apply it to different objects of different classes, and you will get some meaningful different results. Especially it's important for linear regression, because actually this is the way to get some informative results, not just printing results of LM function. And here you get much more than just when you print LM something. You get some residual standard error, you have multiple R squared, adjusted R squared, some F statistics, some P values, and so on. So let's explore actually what we have. First of all, we have residuals. you can get actually all your residuals either by preparing your object. For example, the second item in this list is residuals, and you get this just residuals values. So for every point, you have a difference between the dot and the line, dot and the line. And what will be average value of these residuals if you average all these residuals?
Intercept?
No.
0.
Yeah, exactly. So some of them are positive, some of them are negative, some of them are positive, some of them are negative, but in average they are 0. Here you have like 9.x7 blah 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 year minus 16. It means like really small number, and it would be 0, but computer is not precise enough to calculate such small things. Okay, yes. So mean of residuals is 0. So that's why it's not informative if you calculate mean. So that's why you see here median, not mean. And it shows some potential asymmetry in distribution that is used to assess model quality, but we will not cover it for now. The next thing is coefficients, but now
I'm sorry.
Yeah.
I'm sorry, but is mean 0 or this small number 9.e minus 16? So I did not understand this part.
The problem is that non-integer numbers are represented in computers with some like level of precision. So, for example, when you work with non-integer numbers in R, they're called double. It means double precision numbers. It means that they are recorded with some kind of degrees of 2 and with some dot somewhere, and it means that if you have not integer values, they are represented with some error. It's usually not really important, but sometimes, for example, you get very, very small numbers in some cases, and they're actually meaning 0. So, for example, if you're, I think 2 squared 2 minus 2, yeah, something like that, right? Just, I mean, this one is just the 2, right? Oh, I'm sorry. This one is 2, and this one is 2 too, right? You do something minus something, and you will expect to have 0, right? But because computers are not precise, they give you this like very, very, very small number, because these two numbers are actually recorded with different precision, and gives you the small artifact. So this actually more or less similar to this, right? So you have here like e minus 16.2. So e minus 16.2 means like 0.000000016 zeros.
Okay, so computer first tries to find the square root of 2 with some precision, which is actually not possible, and then it multiplies this number which it found to 2, and then it subtracts 2 and gets some very small number. Yes, so it cannot so yeah, it cannot do this without finding the precise value of square root of 2. So it should find this value, and then when
yeah, so this artifact comes from the fact that you do so you conduct this operation on another value of precision, and then to actually the same values but with different precisions, they're converted from a binary system to how to say, to tens, to a number that represented in our usual systems based on 10 numbers, 10 digits, and it just adds you some artifact when you compare this to when you subtract one number from another, you get some very small difference. So just an artifact of computers, not even R. So you will have more or less the same thing in other programming languages too. So actually, when you want to compare the numbers, you can get this artifact. For example, you can get like if you compare square. So yes, of course. But even this will give you false, right? It's counterintuitive, right? But if you want to like say, okay, I want to check that these two values are basically the same numbers. Like, I mean, without all the things that I explained to you. There is a function all equal that actually will do the thing. How it actually works, it actually checks that difference between two numbers is less than some tolerance value that is calculated based on this machine precision actually. So yeah, it's important to understand that, but now for understanding linear regressions, it's the only thing you need to understand that this is basically a zero. Okay, so let's return to the model. So yeah, residuals. We have some summary statistics for descriptive statistics for residuals. So quartile, median, third quartile, minimum, maximum values. Okay, and we have coefficients. Also for coefficients, you also have standard errors, meaning that you have sampling distributions not only for means, test statistics, but also for these coefficients. It means that actually, like, imagine that in reality, there is some real linear relationship between two variables. At least something that you, like, if you have two populations that you have all numbers, you can really calculate like real coefficients of this relationship, even though it's not linear, but it doesn't matter. If you have all the data, you could have calculated, right? But we have only sample, and every time we run another sample, these lines will be somewhat different, right? So the next time it will be maybe a little bit higher. The next time it will be maybe not higher, but with a big different angle and so on. So in reality, if you do multiple experiments on the same populations, you'll get a bit different results every time, right? And that's why we can actually talk about like sampling distribution of these coefficients, and we can estimate like what is the intercept, what is the standard error for these two coefficients, and based on that, we can even calculate t-statistic and p-value for every coefficient. Null hypothesis here is that for this p-values calculated is that coefficients in general in population are zeros. So in this case, we can like calculate t-value and p-values. We are usually not interested in intercept p-values. And could you explain why? Just try to.
It's always the same.
No, they're not always the same, but I mean, what actually it says, like, yeah, we have, if we have the null hypothesis that intercept is 0, it's very improbable to get these results. But I mean, we don't care if intercept is 0 or not 0 usually. I mean, it is not so interesting. What really interested in is whether the slope is not like a horizontal line. So H0 for the intercept means that in x equal to 0, y equal to 0. But it's usually not interesting for us. Yeah, it's not really interesting for us even it's either it's higher or lower in general. What is more interesting is whether it is there is a line that grows or it otherwise fades with x. So there is a slope, and it's not just horizontal line. So for coefficients, H0 is that this line is a horizontal, geometrically speaking, right? And if you have very small p-value, it means that if null hypothesis holds, and if null hypothesis holds, it's very improbable. It's very surprising to get such estimate such results. So yeah, we're usually much more interested in slope coefficients. In case of more complicated multiple linear regressions, we'll have more predictors, but the logic will be the same. But in this case, in simple linear regression, it's even more simple. We have one line, we have x and y, and we have just one coefficient for a line. And actually, p-value here will be the same in this case with the p-value here. So p-value for the whole model. All right. So yeah, according to the results, we can say that yeah, we can reject null hypothesis that there is no there is a flat line, right? Flat regression line explaining the data. Okay, so what is also interesting here is this multiple R squared. It is the thing that assess quality of the model. So if p-value says that is it surprising to have such data if null hypothesis is true, multiple R squared as well as adjusted R squared says us about effect size. So actually R squared is one of the way to access effect size for the model. We will not cover adjusted R squared for today because it's actually the thing for multiple linear regressions. So we will forget about this now. And for multiple R squared, for simple multiple R squared, it's we'll even calculate it actually. It's not that hard. So to calculate it, what we need to know, we need to take our residuals. Residuals is something that we failed to explain, right? Where I'm wrong? Do you know? What is it?
We have model right, not right.
Right. Thank you. Yeah, we have this residuals, but we measure not residuals. We measure squared residuals, right? So we have ordinarily least squares. We calculate square of them, and we calculate sum. Okay, this is the value of what we couldn't explain. Okay, but now to understand how good is our model, we need to understand what we actually explain. There are many ways to calculate it, but I think the easiest way to calculate it is to first calculate actually what we could explain. What we could explain. We could explain actually sum of squares for y scale. So if we take model right, model right, not model right, sorry, school right, these values, and then we calculate difference to mean, and the same we calculate square for them, and then we summate the squares, right? And this value is something that will be ideal if you explain. I mean, it's maximum that we can explain. That is something that we really want to explain. So it's variability in the outcome that we want to explain. Actually, it's this formula reminds you something? Sum of square difference to the mean. If we divide it by length of the variable. Variance, exactly, right. If we divide this by length minus 1, we will get variance. Cool. It's very cool if you understand this connection between methods. And actually, we'll talk about it a lot, not only today, but today especially, because now maybe you have a question actually how, for example, correlation is connected to linear regression. Do you have any? Do you have such question? I mean, where do we need to use linear regression? When do you need to use correlation? And what is the relationship between them? And it's a good question, actually. It's a perfect question. And we'll answer it today. But first, we need to understand the R squared and where it comes from. So actually, this value is just something like variance. So measure of variability of the data, but not like divided by n, but it doesn't matter actually for this case. Just to simplify the formula. But you can think about that. It's like we have some variability in the data, and we want to explain this variability, right? So we want to have some predictors that explain why these values are low and these values are high. It's some like intuitive understanding of this concept, at least for me. Okay, let's return to this values. It's the maximum. No, it's not the maximum. It's what we couldn't explain. Okay, so now, and what we couldn't explain, also this sum of squares of residuals, it's called residuals sum of squares, or RSS, just a term that is really used. It's usually called like this big letter, RSS. I think because it's mainly it's used, not mainly, but I mean, it's very linear regressions is very used in economics and every crowd guides. They like it will be like RSS with capital letters, and yeah, right. And this is something. This is a variance, but this without division by length -1 is a total sum of squares. It's something that we wanted to explain. So if we divide one by another, we will get ratio of variability that we couldn't explain. And
so can I ask right now why the amount of what we like the number that says, I don't know how to say that, why this RSS is bigger than TSS if we expect it to be otherwise?
No, it's not bigger. TSS is bigger than RSS, but it's a good question. If
yeah,
RSS is bigger than TSS, then there is a problem, right? So yeah, RSS is smaller than TSS. So, but it's
so
good
many
that you
numbers.
It's okay. Yeah. Right. So it's something that we couldn't explain. So now I have a question for you all. How to calculate R squared? From now, we need to do one more step. Remember that R squared is like how much we explained. And now we have how much we didn't explain.
Just to subtract what we obtained from TSS.
Yeah, we can like TSS minus RSS divided by TSS, or just 1 minus RSS divided by TSS. It will be just the same exactly result. And now let's return to our result. And yep, we have the same results with multiple R squared. So now you'll know what stands behind this R squared. So what is in, okay, let's try to understand this R squared better. First of all, what do you think? Is it good or bad? I mean, is it big value or not? Can we even talk about that this value is big or not?
It means that it explained 36% of our data.
First of all, could we even talk about that? Like, can we even talk about that? This values say something about whether our model is good or bad in general. I mean, it's a complicated question. I try to make it more complicated. And if I have difficult question, it's okay to not answer correctly. So don't be shy and talk, please.
I think this is exactly the indicator of how our model good, how good our model is.
It can be used as a assessment of quality of model, right? It's we can even compare different R-squared between different studies, for example. For example, in one study we have 0.35, in another one we have 0.001 R-squared, and we can say which model explains more and which model explains less. So another question is whether this is big number or small number. I just want to hear how do you think about it.
If it would be a large number, so would it mean that we have much confidence in our model or not?
Yes, yes. And first question I think you need to ask when we talk about whether it's big number, small number, what is the maximum number and what is the minimum number? What is a maximum number if we explained like fully, like our model is perfect, then explained everything? What will have in this case? One, exactly. And if our model is completely nonsense, for example, I know we can even try. I think I have some idea what we can use to make a nonsense model here. There is a ID variable. I read some stories from either Quora or Stack Overflow. Like my boss says that if I include ID values or something like I change position of values, model works better. Do I need to find another job or something like that? So if you have something, if you have in your model that your ID can predict something, it's usually something bad actually, because I mean, either your ID is not really ID, but you have some dependency of I mean, the latest, for example, respondents are somewhat different to early respondents, something like that. But if you try get summary on this, whoa, it's significant. Low, but you know, yeah, but p-value is not that big, so it says, yeah, it could be like it could be even worse in 8 cases in 1000, and R squared is very small, 0.003. Actually, it's not that small, because in many cases it will, in some, especially for social sciences, this R squared is pretty much okay, but it's never will be like high R squared. So yeah, that's really strange. Actually, I didn't expect it, really. And yeah, I think it can be because yeah, I think that they added ID after they sorted the variables. So they started with Hispanic race, then Asian, then 2 Hispanic, then many African Americans, then white. And sometimes it is not in the same order because it's kind of strange that they have Hispanic, then Asian, then 2 Hispanic again. But yeah, it's very improbable that it was not sorted anyhow. And because of this, and they added IDs after this sorting, and it explains actually the results. But if you don't have such explanation, I would be very, I mean, I would be very cautious about your data in this case. Okay, so let's return to our normal model. So yeah, do you think this value is big? Do you think that this R squared is big?
But if we compare our normal model with this right and ID model, so in right and ID model, multiple R squared value was like 3%, and here it's 35%. So maybe it is significant here. Maybe it means something.
Yeah, I mean, in both cases, it's significant because when you talk about effect size, and we definitely talk about effect size actually here, it's a different thing to evaluate. Of course, it's connected because if you have the same sample size, if you have the same method, they're just interconnected, right? The higher effect size, the lower p-value. But in general, you cannot say that if you have very low p-value that you have big effect, I mean in centimeters or whatever. So to access, to estimate, I mean like real effect, like real whether something is bigger than something and in what range something is bigger than something, you need to use effect sizes, and for linear regression, it's just R squared. So you explained 35% of variability, meaning that there was some variability, and you explained something like 1/3. Like, not great, but not terrible, right? So it could be better. And in some fields, like if you don't have 0.8 in your model, you're a loser. But if you estimate by that, for example, social scientists, they will be always losers because, for example, they don't have enough reliability in their methods, just because they have a lot of error in estimating, because every time you measure something in social sciences, it usually has a lot of variability. You use, for example, GDP per population or whatever, and all these things are very highly variable and so on, and models, they do not take in account everything. They're always limited. And that's why in social sciences and economics, it's very improbable to get really high multiple R squared. If you go to physics, in general, their R squared are higher. So, okay. And now we can return to a question about how it's all related to correlation. And is it related somehow at all? By the way, before that, I want to show you one more thing about that we using this model, in this model right object that we created, we can not only calculate this p-values r² and so on, we can also do predictions. So predictions are basically just you get by the you see the line by this x, and you, for example, okay, if students have 40 for reading, how much writing you'll have? This, it will just say the value on the line. It will be like 46 or something. And yeah, it actually works like that. So I'll check like model, and you need to provide a new data argument, and for new data argument you need to provide a data frame with the same predictors. So you need to say, for example, red equal to 40, and that will generate your prediction, right? 46, right? Just a value on this line for 40. You can even try something crazy, like what if you have minus 100, and you will get minus 31, or otherwise, what if I have 10,000 for reading? It's impossible value, right? And you will get some impossible outcome. It's just important thing about linear regressions that you can somewhat interpolate within the dots, that within the data range that you provided, but you cannot extrapolate these results because it will give you some nonsense values. Okay, so again, let's return to r², and how linear regression is related to correlation. Because actually in both cases, we have two continuous variables, right? Right. In both cases, we explore how they're related, but we use completely different functions. We use completely different terminology to talk about these two methods. Why? Actually, just historically, if you have one predictor in linear regression, it gives you exactly the same results as Pearson correlation coefficient. We can try like core test, school right, and school read. Right, we have a correlation coefficient 0.59 and something. We have p-value, and this p-value, and believe me, it will be on other data sets too, is exactly the same data, is exactly the same p-value that we have here and here for simple linear regression. Right, I mean, exactly the same. So they're not like similar methods. They basically, mathematically, they are the same things. It's just like different ways to see them, right? And even more, how do you think r² related to correlation coefficient r or core in correlation? Do you have any ideas? Maybe just some like crazy ideas why r² is r².
The square root. I mean, it's
Exactly, right. Yes, yes. So if you take just this coefficient, estimate, I suppose, right, and get square of it, you will get r². So for simple linear regression with one predictor, this multiple R squared is just a square for correlation coefficient. And remember that correlation coefficient can be from -1 to 1. 0 means that there is no correlation, no association, no linear association between variables. -1 meaning that there is absolute negative correlation. The higher is X, the lower is Y. And +1 means the perfect positive correlation. The higher is X, the higher is Y, right? Right. So if you calculate square of correlation coefficient, it could be from -1 to 1. Now this number will be from 0 to 1 because, you know, negative values will be positive and will be the higher threshold will be still 1. So R squared can be from 0, like the model that explains absolutely nothing, to 1 model that explains perfectly everything. And that's a connection, actually. Actually, we can even think about t-test as a form of linear regression, for example. For example, what we could do, right? We can compare, let's say, writing scores for males and females, right? To do that, we need to do like that, school, or we could do it even like that, right? Tilde and gender equal to school, right? But for the example, we'll use not Welch corrected to sample t-test, but original t-test. Var equal room, meaning that just simple 2 samples t-test. And actually we can do the same, but in form of regression. It will have a similar syntax actually. Summary. And look, yeah, we have different confidence intervals and so on, but and it actually even no, t squares actually the same here. You can see, right? And p-values are the same. If you do this test in forms of just t-test, like you compare a group of boys to a group of girls, and if you use it as a predictor, as a binary predictor in a linear regression, you have the same results. So basically, t-test is just a special case for linear regression, somewhat, right? It's important idea. It's important idea that actually not even discussed a lot, because in many cases you learn about like t-test, you learn about ANOVA, you learn about linear regression, correlation. And what do you think about actually ANOVA? Actually, ANOVA is a special case for linear regression too. Actually, I think I will show it later because it is a special case for multiple linear regression. But actually, you can we used, for example, like let's say low, middle, high, yeah, like this, SAS, for example, or race. We used it like this, AOF, and then formula right by s, right? Says, what it says, I don't know, date on school, and you get some results, right? And also you can just change one thing in this line, just change auth with lm, and you'll get the same result. It creates two variables by dummy coding. So actually it shows, it creates two variables because you cannot use categorical predictors for linear regression. But if you have several classes, you can create from one such column several columns, like is it a low class, is it a middle class? And if it's not low class or middle class, it is a high class. So in this case, you like divide some complicated categorical variable to several and use them as predictor. We didn't cover multiple linear regression yet, but you get the idea, right? T-test is a special case of linear regression. Correlation can be considered as a special case of linear regression. Even ANOVA is a special case of linear regression. So all these methods are interconnected. Moreover, they're not actually just interconnected, like, you know, like two entities, like you know, state and church, you know, in non-theocracy. They are, but some autocracy. They're just one thing, actually, and just represented in different formulas and different ways. And it's a very important idea to understand and to have in mind when you think about which method you need to apply. Should we apply t-test, ANOVA, or linear regression? It's very important to know that actually they are one thing, right? It doesn't mean that you can like you have two groups and you say, okay, I will do linear regression. Everybody will think that you're crazy. You will be in theory correct, but people expect that if you have two groups, you show t-test, t value and p value. But if you do a linear regression, you will be not wrong. You just will be harder to understand you to other people. So that's basically all. Maybe you have any questions? Like, I don't know, you change my mind so much that my brain is overheaded. No, something like that.
So all these tests are interchangeable somehow, or
Yeah. So
okay.
basically, they can be considered as a special case of linear regression. And
So
moreover,
we can just learn. So we can just learn. So we can just use one in all the cases if we need it.
In theory, yes. In practice, like peer reviewers or other people will not understand you if you apply linear regression, but you will be not wrong, and I mean it will be correct. Yeah. If you, so yeah, you can do that. Like you can apply ANOVA for if you have only two groups. It will be not wrong, right? We even discussed, I did even show you that the results will be the same. But you know, like if you have two groups, it's like common to use t-test, right? And like, yeah, it's easier to understand. You see t value, okay, you know that it will be comparison between two groups, right? So
will we discuss this ANOVA next time? Because I think we haven't discussed it yet,
Ah,
or I'm wrong.
oh, I thought you. No, I think you are wrong. Actually, I think you're wrong. We discussed an hour previously, so please check previous
Okay.
lectures. No, we discussed it. Yes.
Okay, so I need to.
Yeah.
Yeah.
You can check my materials too about ANOVA. Actually, they're pretty big, but okay. Okay, that's all for now. See you next time. Bye.
Bye.
Thank you. Bye.
Thank you. Goodbye.